All right, let's continue our discussion on memory hierarchy. And today we are going to see some real stuff that is regarding the most important application nowadays, matrix multiplications. But before we start, why are we talking about this and why are we using matrix multiplication as an example? Because matrix multiplication is actually a pretty memory intensive operation, given that if you think about for each byte of data, we have to perform just like half floating point operations, but which means that the time we are going to spend more on memory instead of the real computation. And however, our memory is so slow, so we really need to address that. And modern computers, we all have memory hierarchy to deal with, to mitigate the gap of between DRAM and the processor speed. However, if we don't know how to leverage those facilities, then we are just wasting them. So, so to identify why are we wasting them, we have to know like what are the sources of cache misses. And presumably we have three different types of cache misses that we have to address in a single core program. So these are compulsory misses, which are the cold start misses that means that the first time when we access a certain data blocks, it's unlikely those will be in the cache. So this kind of first time access to a block is considered as compulsory misses. And then sometimes just because our program wants to visit a lot of stuff within a very short period of time, so we will have the trouble called capacity misses. So that means that because the working set, so when we say working set, it typically defines that given a window period of time, how much data has been accessed. And so from our class, it's typically the case that we care about, well, the last time we access it, why this time is also a miss, right? So then that means that the window period we are looking at is that the last time we touched this block and the second time we touched the block. So this would be like a window period. So the window period varies, right? So sometimes, so that's why I don't give a very good definition of the working set size, because it's actually case by case, scenario by scenario. So you cannot really have just one definition that fits all. And conflict misses means that, okay, if there is a miss that is not compulsory miss, is also not capacity miss, that must be conflict misses. But why do we have conflict misses? It's not because we don't have sufficient amount of blocks in the whole cache. It doesn't mean that this is the first time we touch the data. So what does that mean is that, remember, we are running our application on a set associativity cache, which means that your data blocks is only possible to map to just one set in a cache. So even though your cache still have space, as long as we don't have other blocks in the cache within that set, that means that, well, we have to kick out someone. And if your block, unfortunately, was the one being kicked out, then you will have that kind of miss. That's called a conflict miss. So through that, we ran through an example last time, and we know like for this kind of cache, we have a majority of conflict misses. And if you are having a more weight associativity cache, then you are less likely to see conflict misses, but instead you still have compulsory misses. And to address conflict misses, we have, well, so first of all, to improve the access pattern so that we can have more hits instead of a lot of misses, we can do loop interchange. And loop fission is the case where we are dealing with a processor without sufficient amount of weight associativity. And however, if you are in an Intel processor that has a lot of weight associativity, you probably want to do loop fusion to reduce the amount of total memory accesses or instruction count. And today, we are going to do a case study on matrix multiplications, and we are going to combine a lot of techniques together to see how we can ultimately make matrix multiplication very efficient. So let's talk a little bit about matrix multiplication. But before we talk about matrix multiplication, how is a two-dimensional array being implemented in C? So basically, two-dimensional array is nothing but a different view of one-dimensional array. Why am I saying this? Is because if you look at the way how we construct a two-dimensional array. First of all, the top label saying that my two-dimensional array is named as A. Then the top label, I have to allocate a double pointer. So what does that mean by a double pointer? It means that I am allocating an array of pointers. And so what's an array of pointer? It means that, for example, here, I allocated like m entries. So you can consider this m as the number of rows that I have. And however, this m doesn't store anything, doesn't store any data. The only thing it stores is m different arrays. And each of the array in this m, they are actually a row in the matrix. So now you get a list of pointers, and each pointer is pointing to a row. So that's the top level. And to initialize each row, you have to do malloc again. So here you see a number of double numbers being allocated as an array. And typically, in malloc functions, we do the concept of memory pool in a way that if you are allocating data continuously through malloc function, they will give you consecutive addresses in a virtual address space. So what does that mean is that if you keep doing this, the first row is likely to start here, and the second row is going to go after that, and the third row is going after that, fourth row is going after that. So that's why I'm saying, although from the programmer's perspective, it looks like it's a two-dimensional array. However, the real data allocation is actually sequential. So that also explains why in the case of loop interchange, we are seeing that if you traverse data in a row order first, then go to another row, will give you better spatial locality because of that. Now, let's talk a little bit about matrix multiplication. So this is the most naive version of the matrix multiplication. You have a 3-level nested loop, and saying that the first input matrix A with a dimension m times n, and the second input matrix B with a dimension n times k. So based on your mathematical knowledge, you should know I should get a result matrix with the size of m times k. And the code to do this is pretty much like this. I traverse each of the pair of numbers by multiplying a row with a column from A and B. And then the vector dot product result will go into the corresponding cell in C. So that's the idea, right? So if you look at this, right, the vector element-wise multiplication in a vector is actually in this iteration. And then to go through all the pairs of those vectors, you need 2 other levels of the loop. So that's the basic naive idea of matrix multiplication. So algorithm class will tell you this is an n-cubic algorithm. So now I ask you a question. So if I need 2 seconds to run an input size with 1K by 1K by 1K matrix, can you project how much time we would need for 2K by 2K by 2K matrix? Based on what algorithm teacher told you. Eight times, so what's the number? If this is 2 seconds, how much time it would take? 16 seconds. Okay, let's take a look. 16 seconds is not that long, right? So let's run a demo. Okay, so Okay, so here is the naive matrix multiplication code. And now let me run it, and then let's see how much time it would take for different sizes of the matrix multiplication. So here I'm going to run a few different sizes here. Okay, so I'm going to run like 512 1K, and 2K. And let's see how much time that would take for each. Okay, so now we've finished running all of them. So let's take a look. So for the case where we have 512 by 512 by 512, it takes 0.13 seconds to run it. And if we times that by 8, right, which is increasing the size to 1K, right? So if it's 0.13, then we are imagine, how much is that? Probably somewhere around 1 second, right? But then how much we get? 2.4. And now, we previously said, okay, if it's 2 seconds or 2.4 seconds, it probably would be around like maybe 20 seconds. How much time it takes to run 2K? It's actually 24, right? So what does that tell us? The algorithm is not useful, right? Algorithm class is actually not that useful. And if you look at the reason, right, it's kind of interesting, right? So first of all, if you look at the instruction count, it's pretty much instruction count, right? So this is something start with a 1. This is then goes to 8. And then this goes to 69, right? And this is 8.5, right? So with that, you can see that the instruction count indeed goes up with the algorithm arithmetic, algorithm complexity. So algorithm has a pretty good indicator of the instruction count, right? So in the performance equation, cycle time doesn't change that much. However, the instruction count goes to 8 times, right? So if the CPI doesn't change, then the performance should go with the instruction count. So in that perspective, complexity is totally right. However, one big assumption in algorithm always fail is that they assume CPI doesn't change at all. If you look at a CPI, it goes from 0.6 when we have small sample size, and then 1.2, and then finally 1.7. So that's why we are seeing that difference. And why the miss rate, well, why the CPI goes up in this way? Because if you check about the cache miss rate, it starts with 25%, then goes to, when stay about the same, and then goes to 0.3, well, 31%, right? So the cache miss rate is actually one of the main reasons the performance goes bad. So it's really, so we know that cache miss rate is really a big problem here. But what kind of misses are we seeing? What kind of misses are we seeing? So please think about that. What kind of misses are we seeing? All right, let's take a look. So this is what you guys say. So definitely we need some discussion. So why don't you guys go ahead and discuss with friends? All right, so after discussion, more of you think the answer is either B or E. So what's common in B? Okay. E says compulsory misses and conflict misses, and B says capacity misses. So definitely every type of misses has its own advocator. So first of all, right, two types of misses are the most easy to identify. What are those? Capacity and compulsory misses, right? So for this, first of all, right, if we are given this size of data, right, or in general, since we are traversing arrays, right, and compulsory misses only occurs in the very beginning, right? So how many compulsory misses are we going to see here? How many compulsory misses are we going to see here? So first of all, how many memory accesses are we incurring here? How many accesses are we going to incur here? How many total memory accesses? No, this is 3 in each of the iteration, right? So how many in total? If it's okay, so 2 to the 4, 2048, that's 2 to the 11, right? So 2 to the 11 power of 3, that will be 2 to the 33. And 2 to the 33 times 3. That's the total number of memory accesses that we are going to have. How many compulsory misses are we going to see? Remember, what's the definition of compulsory misses? The first time we load data into the cache. So when we go into the cache, what's the unit of that? What's the unit of data when we put that in the cache? What's that unit? Block, right? So how many blocks do we have for each matrix? So this is the total access. Okay, remember this, right? How many blocks do we have for each matrix? So it's actually, how big is our matrix? How big is each matrix? How big is each matrix? Is it really hard? 2K by 2K, right? So that's actually 2 to the 22, right? How many numbers are there in a block? How many numbers are there in a block? 8 numbers, right? Because it's 64-byte block, right? Each number is a double, right? So how many numbers are there in a block? 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 I want to hear all of your voice. How many numbers are there in a block? 8, right? So A is 2 to the 3. So for each matrix, we are going to incur 2 to the 19 compulsory misses. Agree with that? Okay, so we have 3 matrices, right? So the miss rate of compulsory misses is 2 to the 33 times 3 in the bottom, and then 2 to the 19 times 3 in the bottom, in the top. Is this number a big number? It is a big number. This is not a big number. This is close to 0. Do you agree with that? So if you look at this, do you think compulsory miss is going to be the majority? Right? This is close to 0. And our miss rate is 33% for now. Right? Something else. So what's the second most easy to identify type of misses? Capacity misses. So how big is our cache? How big is our cache here? 48 kilobyte. Okay. So to run the code, we said that we are going to run 1 row and a column. How many bytes do we need for a row or a column here? How many bytes do we need for a row or a column here? How many bytes do we need for a row or a column here? How many elements are there in a row? How many elements are there in a row? 48. How many elements are there in a column? How big a number is? 8 bytes. So how many bytes do we need for a row or a column? 8 times 2048, right? That's actually how many? 2 to the 14, right? Or say this is like 16K, 16 kilobyte. We have a 48 kilobyte cache. How many rows or columns can we store? How many rows or columns can we store in a cache? 3. Is that enough? Not at all. So what's the majority type of misses here? Capacity misses, right? So here's the thing. If you check the amount of data that we need to store, right? Each row takes 16 kilobytes. Each column also takes 16 kilobytes. No matter you start with a column or a row. And also you have to store the result, right? Result is also a row, right? So just doing one time, you are going to kick out your original stuff for sure. Because we just don't have sufficient amount of capacity, right? So it's very unlikely you are going to keep all of them in a cache. Because each row or column is just too big. So that's why you see, like, when my cache size grows, my CPI keeps increasing. Because they are getting closer and closer to my cache capacity. And in fact, this is just L1. And if you have a good enough mass, you already know simply 512 is already surpassing the capacity of the L1 cache. And the reason why CPI is increasing is because when you grow this size up, you are going to saturate your L2, L3. Eventually, everything goes to DRAM. So that's why you will see a consistent increase of your CPI, because it's going to be more likely we are going to have L2 misses, L3 misses, or something else. right? Which make our performance goes even worse. So the thing is that if we really want to reduce the capacity misses, right, we have to think about if there is a way we can reduce the amount of data that we have to visit in a short period of time, right? Remember the definition of capacity miss is what? The working set size between a window period of time is surpassing the capacity of the cache. So what we can do is that, is there any way we can reduce the amount of elements that we have to visit, have to calculate, have to work on within a short period of time, right? But for this question is indeed the capacity miss, right? So it's not compulsory misses as I show you. The compulsory miss rate is actually significantly lower than 1%, right? And it's also not conflict misses because right now capacity misses is actually the main thing. So fortunately, it's possible to do that. I know a lot of you hate this kind of symbol representation, and you're probably surprised that you are going to see this here. But here's the thing, right? If you consider what is matrix multiplication, it's indeed for each element Cij, it's the summation of aik times bkj, given the k goes from 0 to n minus 1, and is the size of the number of columns in A and the number of rows in B. That's the definition of matrix multiplication for each element. This we all agree, right? But interestingly, right, this summation, you can actually break it up in a way that, okay, if I separate it by 2, right, you can make them, well, that's the beauty of the math, right? Use different symbols, you can represent the same thing in different way, and that would give you another view of things. You can actually separate them by half, and you will figure out that, okay, this is equivalent to, first, I calculate half of the vector from the column and half of the vector from the row. Plus, half of the vector from the column, half of the vector from the column and the row, and then plus the other half of the column and a vector from the half of the vector from the column and a row from each matrix, right? Do you agree with that? Right? The only thing that won't lie to you is mathematics, right? So this doesn't lie. Now, we can further break it up, right? It could be a quarter vector multiplication, dot multiplication, dot product, plus the other quarters. Agree? Right? And then you can keep expanding it in a very unlimited way. Agree? That's matrix multiplication. So what does that mean? If every time I only consider performing a smaller fraction of dot product, then what does that mean is that within a given window period of time, I can work on a smaller piece of rows and columns. Do you agree with that? So if you follow that philosophy, that would reduce the working set size of matrix multiplication efficiently. So here is the concept of tiled matrix multiplication. So right now, instead of going all the way through the end of a row or a column, let's do the case where we just do it quarter by quarter. So in this way, the first run of the algorithm, I only calculate the first half of the A and the second half of the B. And then the next time, so this part, I will get a quarter partial product result for the Cij. Instead of going through other things, right? The next thing I'm going to do is that, okay, let me work on the quarter result for Cij plus 1. What does that mean is that all I need is to reuse the same A, but just fetch one more part of the B. And then I will keep doing this until I reach the boundary of the size, the partition that I have, right? As long as this partition fits in my cache capacity, as long as this partition plus the same size of the partition and this partition fits in my capacity, we are not going to see capacity misses when we run this. Do you agree with that? Right? So if everything falls into the capacity, right, I can guarantee one thing is that now, if I want to calculate this element with its quarter dot product result, right? I can fetch another quarter row or half row from matrix A. And because to calculate this, all I need is this part, which is already in a cache, right? Am I going to see a miss? I'm not going to see a capacity miss anymore, right? Do you agree with that? So the good thing about partitioning the matrix multiplication into different parts is that we can ensure now every of this sub matrix, or say a tile multiplication, they can fit in the size of the cache. So then we can eliminate the capacity misses if we choose the size properly. Do you agree with that? Okay, so now, so if you want to get a complete result, right, you will continue doing the iteration in a way that, okay, so if I want to do this part, right, then I can still reuse this, just fetch another tile from the bottom part of the same matrix, right? So you might think about, then I'm going to kick out that, right? I mean, because you have limited capacity, so there's nothing you can do with it for sure. However, in the meantime, when I am calculating these elements, I don't need them for a long while of time, right? So it's okay if they miss it, right? So, and then if I want to finish the calculation of this part, again, I have to refetch this part, but and fetch another tile, right? So gradually, I'm going to cover all the matrices, but every short period of time, I'm only working on either this tile plus this tile, or this tile plus this tile, this tile plus this tile, or this plus this, which all fits in the cache, right? So it's a lot better than every time when I finish working on the line, it's all kicked out. Do we agree with that? Right? It's anyway better, right? So if we want to run this kind of algorithm, right, this is the resulting algorithm we are going to do, right? Remember, each time when we run this times this, it's pretty much like we set a boundary, right? Starting with the lower bound of this matrix tile and multiply by the boundary of different matrix tiles, right? So this inner part is pretty much like a smaller matrix multiplication with boundary. And the outer tree level of the loop is basically changing the boundary of this matrix tiles. And so the difference is that each time I'm incremented by the size of the tile, right? And here I'm still incremented by just 1, because here I'm doing the real smaller matrix multiplications. And here I'm doing the shifting of the tiles, right? If you don't believe me, count the total amount of matrix multiplication, the multiplication and summation we are going to do. It's going to be the same. And this is actually the implementation of this mathematical equation that I gave you. So now, given we know this is the implementation, right? And the criteria of this to work well is that, first of all, we have to make sure each tile fits in a cache. And if we have 48 kilobytes of the storage, right, we can pretty safely assume that we should reserve 16 kilobytes for each of the tiles, because we have C tile, A tile, and B tile. Agree? So if that's the case, right, given that we have 8 bytes of data, then 8 bytes of data in each element, right? Roughly, you probably can have your tile size as big as 45. Agree? So now, like 45 is definitely going to cut a lot of boundaries. So what if we just pick it at 32? Do you agree this is the tile size that won't cause a lot of capacity misses? Do you agree with that? Agree? Okay, we are good at that. Okay, so let's look at a demo. So now we have a tile matrix multiplication. Okay, and here is the exact algorithm, the same as what the slide shows, right? And we are going to run it. And let's try with tile size as 32. And let's see how does that compare against the baseline, which is not a tiled version. Okay, still takes quite a while. Surprise. I thought it's going to be really fast, isn't it? Why is it so slow? Is my computer slow? Couldn't be. What happened? Hello? Are you there? Are you there? Hello? Okay, here we go. Okay, so, because I also run one more. So here's the thing, right? So let's take a look. So this is the original run we have, right? You still remember those numbers, right? So let's compare. If we are doing 512, originally the runtime is 0.13. Right now it's only 0.07, right? 2 times speed up. 1K, originally 2.4. Now how much? 0.62, right? And if you would like to do a math, isn't it close to the 8 times of this 0.007, right? Now, this one takes 23. How much it takes here? Only 5, right? And if you multiply this number by 8, isn't that close to this, right? And if you look at the CPI, it's indeed quite close, right? But you also see it's getting up. And if you check the data cache miss rate, you still have 20%. You still have 20% of data cache miss rate, right? So we have been improving a lot from 25, 23, 31 to 22, 21, 20, 21, right? And that's why we get a CPI that's a lot lower, right? Originally it's 0.62, now 1.2, 1.7, and everything here is close to 0.4, right? So this tells you sometimes, right, just a drop of this like 4% of the miss rate would actually give you a significant bump in CPI. It also tells you how slow a memory access is. But now the problem is that where are we still seeing this 20% of the cache misses. All right. So most of you think the answer is C. What is C? So why don't you discuss with your friend and justify why you are having the answer as C? Because like most of the time people pick C, they think that's probably a reasonable guess, right? So why don't you guys just like discuss with each other? Why is C? All right, I guess. Okay, very good. But why? I want to hear from some of you. Okay, that's a very good thing, right? So, I feel like I did a bad thing in a way that I kind of like told you how to tell the answer really quick during the exam, isn't it? Right? So during the exam, all you need to do is like make sure this is not a compulsory miss, not a capacity miss, conflict miss, right? If that's a miss, right? So this is probably what you did, right? So first of all, but that's good, right? Because now you learn it, right? Every tile fits in a capacity, no capacity misses. Previously, we have calculated the amount of compulsory misses is super low, super tiny, right? So this couldn't be, it cannot be, right? So it must be conflict misses. But let's look at the reason why we are seeing this conflict misses. So first of all, if you do a partition of these addresses, right? And let's take a look. So for A, because we are doing sequential access going through a row, so we have pretty good spatial locality, and most likely they are going to be in the same, like just a few blocks, right? So thinking about this, right? They are typically just in a few blocks. And the other thing is, if it's a sequential address, if your math is good enough, if it's sequential address, it must be in a set that is different from the previous block. So sequential blocks, they are typically in incremental set index. If you don't trust me, it's the numerical theory you can prove. And this is true forever, right? Longer than your love. So the thing is, for A, we don't have to worry about the conflict misses. If you see a misses on A, that has to be capacity misses anyway. Now, let's talk about B. So for B, we are doing the traversal order of a column. So if you look at a column, right, the first element, so because we have 2K elements and we said we are storing data consecutively. So you can, in rows, so you can assume for each column, their address must be this amount apart from each other if they are at the same column index, the same row index. So for, in a different row index. So saying that if I have B0, 0 at this address, the next row with the same column index, they are actually going to be this, right? And incrementally. So this sequence of address, are we all okay with that? And then if we make a partition, you will figure out they all have different text for sure, but they surprisingly all have the same set index. So what does that mean? When I try to fill in this column into the cache, what I will see is that, okay, goes to index 0, goes to index 0, goes to index 0, goes to index 0. And then when I'm fetching the 12s, what happened? It still goes to index 0. So I have to start kicking out the first element in the same column, right? And this is not just the first element. It also covers the next element, which is the next column of the B, right? So then, every time when you access B, it's not likely the column of B is going to be kept in the cache because it was here before, but when we do this, that is kicked out. Right? So whenever I visit a new row, it's a new column, it's going to be a miss anyway. Right? And it's really bad at this point because simply 12 elements, it will create 12 blocks, go to the same set. And that will clear up almost everything in the same set later on. Right? And the capacity of the cache is still a lot, right? So 32 is actually a bad choice in this situation because you are going to suffer a lot of cache misses on B, even though you have pretty low cache misses on A and C. So that's why you are still seeing like a 20% because of this, right? So all the rest, they will become conflict misses. So the answer here is conflict misses. Now, it's probably not too difficult for you to imagine. What's the solution? What's the solution? So the thing is that, okay, since we are going to have that whenever we meet 12, right? So just make it smaller than 12, right? So what if we do it in 8? Would that reduce all the conflict misses? Right. Okay, awesome. Let's have the demo, right? You probably already see it. I have the tile size A here, right? It was here for a reason. And let's see how the tile size A is going to give us. See, I still have a lot of optimizations to show you. I would say this is probably the most useful lecture. Well, 2 of the most useful lecture. Well, 3 of the most useful lecture for your rest of your life. It still take a while to run because here, a few things that I'm doing. First of all, I'm trying to run through tile size equal to A and then a set of different tile sizes. Okay, let's take a look at that, right? So now, see the CPI is even lower, right? 0.2. And the execution time, 0.5, 0.4, 4 seconds, right? And then 37 with 40K, right? So it's a lot faster than the past. And then the miss rate. How low is the miss rate? Lower than 1%, 1%, 1%, 1%. Right? Only 1% miss rate. Only 1% miss rate, right? So, but you might wonder, okay, so I'm assuming the CPI should go further down, right? Why is it still not doing as well as I would imagine? Why is it still not doing as well as I would imagine? So one thing that you could check, right? So let's compare this implementation with other tile size. So let's take a look. So 32 was the original tile size that we picked, right? And 8 is the tile size that we have now. So for 2K at 8, we have 4 seconds with miss rate close to 1. This one, we have 5.3 seconds with miss rate close to 0.2, right? However, what changed? So our CPI is actually getting better. But what's getting worse? What's getting worse? What's getting worse? Instruction count, right? Because previously, you only need to go to the outer loop control every 30 times, every 32 times. But now you have to go to the outer loop every 8 times. That increases the instruction count, right? So that limits the growth, or say the improvement of our execution time. So in fact, if you look at different tile sizes, you will figure out that although at tile size 16, we get a 7% miss rate. But because the instruction count here is lower than 8, and the miss rate is lower than here, so it actually gives us the best runtime for 2K. Didn't you see that? Right? So this is only 3.6. So another lesson learned here is that, again, you can never ignore the effect of instruction count, right? So that's why go back to the very first few lectures, we talk about what's wrong with flops. They never thought about instruction count, right? So for these cases, we improve the CPI, right, to this, right? And we also improve the miss rate to this. However, the instruction count actually hurts the performance compared against this case, right? So after a certain point, you have to find out the balance between the cache miss rate and the increment of instruction count, right? So, but here, the second thing is that if we want to reduce the conflict misses, we need to ensure an appropriate tile size that shouldn't lead to lots of conflict misses in sets, right? So that's the problem. Okay, so there are still few things that we can do to optimize the code, right? So first of all, if you look at this, right, it seems trivial that we always have to put stuff into the CIJ. And this statement is actually going to trigger a memory access. to put the result into the C, ij, right? Is that necessary? Is that necessary? So every time I'm doing a memory access when I do this iteration, this is not necessary. Okay, how to make it not necessary? Okay, you can just put it into a variable, right? So the right thing to do, okay, so if you know C good enough, the philosophy of C is that if you have, okay, so here's the general guideline. If you have an array, you describe it in an array, that's typically memory accesses. If it's global variable, very likely memory accesses. If it's local variables, that's where the C will try to use register allocate for the value as much as possible. So what you need to do is you can put a variable here, and this variable has to be declared locally in a code so that the C will try to make it a variable, a register. Now, with this as a register, right? When we do this, everything is putting into a register, right? And then only this one would trigger the real memory accesses. Do you agree? Okay. So let's see, how would that help? Okay, so let's try to use a register for that, and let's see how much it would help. Oops. Wait. Why am I? Oh, okay. So I'm doing. Okay, it should be right here. Never mind. Okay, let's try to see. So remember what we got for now. The best is 3.67, right? And let's take a look. How would that help us if we try to store the temporary result in a register? Oh my God, I have to run the whole thing again. Okay, what if I just restart? Okay, let's run it. And let's see how does that go. Sorry, a waste of time. So now in this demo, I'm still going to do different sizes. And let's see what's the number we are going to get. You know, I kind of like feel that I should have the previous. I should also have the previous as, okay, so here we go. So, but in the meantime, what if I just add the previous as a reference? Insert cell above. Oops. Okay, so this is the previous, and this is the one we have for now. And let's see the difference. Let's see what the performance looks like. So for now, right, let's look at 2K at 16. Wow, it's bringing further down, right? From 3.67 to 3 only, right? Significant improvement, right? Remember, previously it was 3.67, but right now it's only 3, right? And the instruction count significantly improve, right? Because we reduce the amount of memory accesses. And one more thing to say. When I compile this program, they are all use -03, highly optimized. So that's another thing compiler won't do for you. If you say I want to access the array, compiler doesn't know if I can change it to a variable. So that's why, as a programmer, you have to do the work. Now, another thing that I want to do is matrix transpose. And the matrix transpose, so one of the issue we have here with conflict misses is because we are traversing in the column order, right? But we are not going to see conflict misses if we are traversing in row order, right? To make that happen, what we can do is just transpose the B array in advance. So this is something similar to something we have done before, is that we sort the data and then run a query, right? And here we are adding one more step, transpose a matrix, and then run the code, right? So as you know, like here, I just need to change the element that I traverse. So how would that help? So that's check. So now let's plus everything together, right? So let's see. So this is the original code, and this is the now let's run the transpose the code. Oops. With different sizes, and let's see what the performance look like. And this also plus no, this is not. Okay, so this is simply the transpose. So let's see the effect of each. Wow, that's crazy. Okay, so if we just transpose without using the register-based optimization, oh no, okay, I'm so stupid. Restart. Is there a wrong restart and wrong? Oh, okay, that's what I want. You know, sometimes if you are doing your assignments, restart and run O is a pretty good function to use. Okay, sorry about that. So let's run everything. So the first version is we just do matrix transpose, but we don't use the register optimization. So you are still storing data in C matrix every iteration. But with this one, we can see what's the sole effect of matrix transpose itself, right? And the second run, we are putting matrix transpose plus using registers. And let's see what's the effect of using both. Okay, so now we have the first set of result being ran. And then let's take a look. So, see, with matrix transpose, we have break the 3 seconds limit, right? Like for 16 tile size, we get 2.63. And this field, and also the cache miss rate drops from 7% to 2% only, right? So it makes the result better, right? Now, let's take a look. If we combine this together with register-based optimization, how is that going to be? So if we use register, see, now, not even 2 seconds, right? It's just 1.9. And the other thing is that the tile size is now good at 32, right? And this is reasonable, right? Think about this. Right now, you don't have conflict misses. So what again determines if you are going to have a miss or not? The capacity, right? So what does that mean is that if we use matrix transpose, it would help us to eliminate all the conflict misses, right? It's going to help us to eliminate all the conflict misses, right? So, and the other thing to mention is without those conflict misses, it actually will allow us to work on even larger tile sizes. As you already see, now 32 becomes the best, right? So, and 32 is pretty much the tile size that we initially got for the capacity for not having the capacity misses, right? So with these pieces of code, you can be pretty confident that the only type of misses that we are going to see is compulsory misses. Agree? So now, right, remember, do you experience that? From 24 to 2, we have got 24 times speed up, right? And all we need to do is just make the code more cache friendly. Okay. And the other thing is that so far we are assuming the tiles has to be square, right? But tiles doesn't have to be square, right? So if I can, for example, here I'm trying to create a rectangular tile, would that give us more performance advantage? So here I'm having the demo with wait, where is my code for a rectangular tile? Wait. Oh, rectangular. Okay, so here is the rectangular version of the code. So as you can see, I have the tile size X, tile size Y, which shows it's a rectangular one. And here, instead of just having one specific tile size, I can create like 8 by 8, 8 by 16, 16 by 16, 32 by 16, or if it's 32, oh shoot. If it's 32 by 32, it means it's a square tile, but we already have that number, so I don't want to run it again. And let's see how does that go for us. But in the meantime, what I should do is that I should have a reference of cell. Insert cell above. Okay, in the meantime, I can show you the, do we have that? Okay, we don't have that. Okay, I don't remember that name, but you have a rough idea. It's less than 2 seconds, right? Let's see. What do we get? So right now, let's take a look at this. Right, previously, I think our best is somewhere around like 1.9, 1.9C or something, right? But right now, we get a 1.87, right? So we get even better, right? And it's 16 by 16 at this moment, right? Or like 32 by 16, that's like 1.88, right? So you get more options to export now, right? With like different tile sizes, with rectangular tile sizes. Okay, one last thing. So take away here, right? Wow, block tiling can help us to reduce the capacity misses and conflict misses, right? Matrix transpose would help us to eliminate the conflict misses, right? Using registers whenever possible can help us to reduce the memory accesses, right? Just using one matrix multiplication optimization example, we learn a lot. Now, the only misses that we didn't talk about how to reduce is what? Compulsory misses, right? But is it possible to also eliminate compulsory misses? No? Okay. So in fact, there is a mechanism called prefetching. So the idea of prefetching is like this. So first of all, your data has good spatial locality, right? So right now, if I want to access a vector, what will happen is that, okay, the first element is a miss. And then I have to wait for the lower level memory hierarchy to get a block, send it to the cache, and then I will have 7 other hits, and then another miss, right? And the same process repeat again and again. However, the concept of prefetch is this. I see you are accessing vector 0. And I know your code must have good spatial locality. So this one is a miss. Okay, I let you miss, right? However, now, you're not accessing or using the L1 and L2 bandwidth, right? And I know you are going to access vector 8 at some point. So what if I just use this period of time to insert a command saying that I want to fetch vector 8, but right now I'm not going to use it. Just put it in the cache. And then when I access 8, it's going to be here. No compulsory misses. What? Right? So here's the thing, right? If you want to reduce the compulsory misses, you can manually insert this command in x86. This is like the C intrinsics. Or this is something the compiler can do for you, right? Because prefetch, as we said, prefetch only get the data into the memory. We are not going to modify it. So this compiler is okay. I feel like, okay, since you're not going to touch it, I just put it in a cache, fine. Okay, let me do it. So prefetch, there's a flag you can add when you compile it. And let's see. So here I have a pieces of a code that I use. And this is like a very nasty, ugly code that you probably never want to write. But this is by far, I would say, the most efficient version of matrix transpose, because you remember our computation start with transposing the matrices, right? So here's the thing. If you enable the prefetch, then it will reduce the time we spend in transpose by 10%. But you might wonder why it's 10%. Because don't forget, what's the miss rate of the compulsory misses? Only 10% when you want to transpose it, right? So it has a pretty low initial compulsory misses. So that's why most of the time people don't really do a lot of prefetching, because only if compulsory misses is the least thing that you can deal with, right? So here's the thing. We also have prefetching to help us on compulsory misses, right? So now you get all the information, right? All type of misses. We have a software programmer's technique. And this is what we are going to. So these two topics, performance evaluation, cache, how to optimize your code, is what we are going to cover in your midterm. So for the midterm, when and where. So first of all, I only see 28 of you get scheduled for the midterm. And this is a class with 41 students. So I guess there are probably 12 people, 13 people. You probably don't want to take the midterm. You want to give up the 15% of the grade. If you are going to do that, I'm fine with that. But if you are not going to do that, make sure that you have scheduled through this website. And only this time slots between 18th and the 21st is available. And every slot has limited seating. So the later you book, the earlier you have to take the exam. Okay? And the testing center will handle all the testing related things. So you are responsible for being there on time, follow the rules. And if you need additional assistance, call the testing center. Contact the testing center, not me, because I'm not going to be there. Only them can help you, right? And no cheat sheet, outside material allowed, 45 minutes only. a pretty short test, and I took it myself, 17 minutes for me. So you might be able to do it. And what we have is 12 multiple choice questions. Each of them should have just one answer. And we have short answer questions. If you have already done your practice exam, you know what kind of short answer questions it look like. And for assignment style free answer questions, like you are going to do like C equal to ABS or calculate the miss rate or something, right? Closed note, closed book, no outside materials allowed. So 12 multiple choice questions. So here I'm going to give you some practice, and you can, like after you have done all the reading, you can go through all of them again to see how good you are. And I'm sure if you can ace the sample midterm, you should be able to ace the midterm as well. Don't like trust me. Okay, so like this one already saw, right? This one, this kind of stuff, right? So these questions, they all look familiar, right? Because they are all on our slides. And remind yourself, what is MDOS law? What's the limitation of compiler optimization? What's the CPU performance equation, right? What's the difference between latency and throughput? And why T-flops is not a good metric. Free answer questions, right? Like, performance equation. This is a big part, so definitely we would have them. Speed up, we would definitely ask you to evaluate it. MDOS law, right? If I give you a few different options, which one is the best, right? Like, if I give you a cache configuration, how many sets, how many offset bits, how many index bits, how many tag bits are there, right? If I give you a set of addresses, I give you a certain cache configuration, can you tell me how many of them are hits, how many of them are misses, and for each misses, can you tell me what type of misses is that, right? So don't ask me or anybody on Piazza for an answer, because all the answers you can find on the slides. You can find all the answers on the slides. So this is some homework that you have to do by yourself. I'm not going to check if you have done it, because when you take your midterm, that's the time to check if you have done it or not. So again, we put all the attendance grades, your current assignment grades, and the calculation since on this places instead of Canvas, because Canvas has a lot of, is pretty buggy. And assignments 2 due this Sunday, it's really helpful for you to get a good idea about what's going on in the memory hierarchy session. And reading quiz 5, don't forget, it's due next Tuesday. So it won't take you too much time, I hope. So just make sure that you submit that on Grayscope question. Okay, if not, I will see you next Monday.